Hi there, this is a follow-on on the previous video of my review of the HDS272S covering a few missing bits. If you have not seen it, there's a link in the description. Let's start with the software CD that comes with it, containing the manual and a program to control the HDS272S from a Windows PC. Plugging the HDS272S USB cable into a Windows 7 machine results in a failed attempt to install the device driver. This is not surprising, as we shall see later. In any case, this is anticipated by OVON in the documentation, and they recommend to install their device driver like in the bad old days where every device had its own driver. Trying to follow the stated instructions is not working, because Windows can't find a driver in the CD despite that there should be one there. And that is no surprise, because for whatever reason OVON stored it as a compressed RAR archive called usbdriver.rar and not as a directory that Windows can search. So what you have to do is to copy the RAR file onto your computer and use a program that can decompress RARs. I used 7-zip for that purpose, but unfortunately did not capture the action on video. But here's the result. A folder called USB driver, which contains another USB driver. Okay, that was me using the extract to here option on 7-zip, but it's not a problem. And here are the important folders. One driver folder for Windows 2000 and XP, and the other folder with a driver for everything since XP. Pointing my machine running Windows 7 at the Win 10, Win 8, Win 7 Vista folder finally succeeds in installing. Sorry, I lost some of the footage for some reason. And in the device manager, instead of oscilloscope, we now have USB device, but according to the installation instruction, that is supposed to happen. Next, we have to install the DS-Wave HOS software, which needs administrator rights, and after a short wait, we are ready to give it a whirl. I must admit, this program had me utterly confused for a while, and I skipped right to once I got somehow the hang of it. As far as I can tell, there are two ways of getting the HDS272S scope screen shown in the program. The first is when you press the button called Get Data. This function takes a single snapshot of data from the scope in form of a binary file in a proprietary format. They are small but accumulate, so you may want to purge them every so often. To get another update on the screen, you repeat the process. If you get tired of doing this, you can instead select the continuous data download, which does the same thing but automatically, and the files are not stored. With that, your screen is refreshed every 3 to 4 seconds. The effect is that if you change something like the volts per division setting, the effect lasts only until the next update, because this only changes the display on the PC, not the HDS272S, as you can see. If I change the time base, there are not enough data points in the last update file to fill the screen, so the PC picture is squashed until it's overwritten. Even when you turn automatic updates off, this is a clear limitation when you make changes in the view on the PC, but at least now the image doesn't get reset every few seconds. The limits of the program become very obvious when the scope picture is changing. In this case, I'm sweeping the frequency of the sine wave in channel 1, and since channel 1 is used for trigger, channel 2 is no longer in sync and unable to show a steady waveform. On the PC, we get successive snapshots showing the situations at random moments in time. Interestingly, these are obviously taken after a complete acquisition cycle, so we always see a steady second channel, which only appears as a blur of many unsynchronized updates on the real scope screen. However, if you did not know, you would not be able to tell from the PC picture what's going on with channel 1. You can actually remote control the scope settings, but only when the auto update function is not running, so you won't see the effect on the PC. I can change, for example, the vertical resolution for a channel, in this case channel 1. Or the time base, which of course affects both channels. Using the To Mathematics button, you can select a choice of math functions that can be applied to the signals from channel 1 and or channel 2. The green curve is the sum of channel 1 and channel 2. And now the difference. One problem I found is that, for example, channel 1 times channel 2 is way too large, but there isn't really a scaling function for the math function. The fields that I assume are meant for this are not working. Anyway, let's get back to showing the sum which fits on the screen. Math works even when auto update is running, so when, as in this case, the phase shift between the two channels is changing, the green math curve changes as well. But since the update cycle is only about once every 3 to 4 seconds, I show this much accelerated. You only wish it would work that fast in reality. Similar to math, there's a fast Fourier transform button, but I did not have much luck with that. Clearly something appears when enabled, but whatever I tried, showing somewhat accelerated here, I could not get this to display properly, despite trying out scaling and Hamming windows, options and whatnot. The invert function works as you would expect, and like math, it even continues to work when you enable auto update. And I hope with that I've given you enough of an impression of what the PC software can and can't do. This was version 1.0.4 by the way. Overall, I was not too excited, especially with the slow update rate and the inability of remote controlling the scope while getting updates. And with respect to that, OVON prevents you from running the remote control window if auto update is already running. But nothing stops you from turning auto update off, then starting the remote control window, and then turning auto update back on, except, oops. Time to move on to a fresh install of Linux Mint 20.2. With the OVON plugged in, the kernel messages show it as an oscilloscope like it did initially on Windows, but the usual messages about setting up an HID or human interface device for it are missing. It is listed as a USB device, but if we ask for more details, it is obvious that something is wrong in the way the HDS 272 reports itself. There's an unrecognized sequence of bytes in the interface descriptor, which leads to the overall verdict that the device could not be opened. I tried various things to get Linux to recognize the OVON in its HID mode, but nothing worked. I guess we have to wait for an update from OVON before we can use the HID interface, which for now rules out doing remote control from Linux. Luckily for me, the scope has a second USB mode. Using the Systems menu, one can switch it from HID into MSC or Mass Storage Device class. In other words, it behaves like a USB stick for either Windows or Linux systems. With MSC enabled, you can hit Save and select File, which shows a few options. The type selects the format as either WAV or image and whether you want channel 1 or channel 2. Let's go with channel 1 and hit Save. And we get a misspelled success. On the Linux system, the scope in MSC mode shows up as an 8.1 MB USB stick, and we see the freshly saved wave1.csv. Note that the time and date is wrong. This is because the HDS 272S has no real-time clock. Also, doing another save with the same name will simply override the earlier one, but I have to warn you that both Linux and Windows tend to cache the old file content, so to be sure to see the new content, you need to remove and reattach the USB cable. The file itself is in CSV or comma-separated value format, which means it can be opened in Excel or in this case LibreOffice with no problems. The top shows some information about the channel, more about that in a moment. This is followed by 8000 entries, assuming you have enabled the 8K memory size in the scope's horizontal setup options. Let's have a quick look at the data by selecting it and charting it as an XY scatter plot. Nice! The header contains an interesting value called voltage per ADC value of 20 millivolts in this case. If you remember, channel 1 in the scope was set to 500 millivolts per division, and there are 8 divisions on the screen, which means 4 volts as the total visible vertical range. That would give the ADC 4 volts divided by 20 millivolts equals 200 steps. I'm pretty sure they use an 8-bit ADC, in other words 256 steps, which means the actual range in this case extends slightly beyond the visible area to 5.12 volts. In practical terms, the 8-bit ADC means that the yellow sine wave spanning 1 volt peak to peak on a scope is sampled into just 50 different possible voltage values, which isn't all that great of a resolution. So if you don't need to see two channels simultaneously, it makes much sense to position a single waveform in such a way it spans as much vertical space on the screen as possible. For the rest of the header fields, the frequency, period, peak and average are not always filled in. I think it depends on if you have measurements enabled but not necessarily displayed, as you can see that this scope picture doesn't show visible measurements. You notice that while the plot clearly shows the sine curve, we see more of the wave than what the scope screen shows. Also, there is some weirdness happening at the end. O1's PC software, on the other hand, for all its flaws, did show the picture that was pretty much identical from what was on the screen. For this reason, I decided to fire it up once more and compare its views with the CSV dumps obtained by saving the wave. As a start, here is a 1 kHz rectangular wave in the O1PC utility set to 200 microseconds per division, for which the scope uses 2.5 megasamples per second, and then the same in Excel using the method of saving the waveform as CSV file. I did the Excel stuff in an earlier run because the O1PC utility needs hit USB mode to work. Anyway, we can see roughly the same picture, although the Excel picture seems to be phase shifted for some unknown reason. Another observation is that the shape at the very right, at 8000, is not correct. The line should have continued horizontally with a negative voltage instead of jumping up. Increasing the frequency to 10 kHz with the scope set to 20 microseconds per division causes it to use a sample rate of 25 megasamples per second. The picture in the O1 utility and in the Excel files are nearly identical to the 1K test before, with the same phase shift and the problem on the very right at sample number 8000. 100 kHz now with a scope set to 2 microseconds per division, causing it to use the maximum sample rate of 250 megasamples per second. Now the phase shift in the Excel file seems to have gone, but the problem area on the right has grown a bit. Basically, from sample 7000 onwards, the picture is not correct. Moving to 1 MHz now, with a scope set to 200 nanoseconds per division and 250 megasamples per second. Obviously, the Excel file contains a lot more than what is shown on the O1 utility and the actual scope screen. But watch this, if I edit the Excel plot to only show the first 600 samples, we get a picture that apart from the phase shift is identical to the one on the scope, including the level of detail. Lastly, 10 MHz with a scope set to 20 nanoseconds per division and 250 megasamples per second. The Excel file seems to contain a solid block, but if I edit the Excel plot to only show the first 60 samples, we get a picture that is close to the one on the scope. This is all very nice, but how is one supposed to know whether one should look at 6000, 600 or 60 entries in the CSV file? To make sense out of it, we need a crash course into what sample rate and trigger settings really mean. To help me understand what was in the memory and what was on the screen, I used this yellow staircase wave on channel 1 because compared to the sine wave, the staircase clearly shows where you are in the wave, and I made it to take exactly 320 microseconds for one set of stairs. The scope is triggered at the lowest point of the staircase using the rectangular signal on channel 2. At 20 microseconds per division and 8000 memory entries, this wave fills exactly the full memory. It is worth explaining how the O1 shows in the top row the relation of the visible screen to the sample memory and the trigger point shown by the little triangle. We have the line representing the memory, which holds 8000 samples. With a sample rate of 25 megasamples per second, that represents 320 microseconds. The visible screen is shown by the square brackets. At 20 microseconds per division and 12 visible divisions, this represents 240 microseconds or 6000 samples. The screen is centered on the memory. Another way to look at it is that the visible screen goes from 1000 to 6999 in the memory, so picking the first 6000 entries I showed earlier was not right. I mean, it contains valid data, and if it's a repetitive waveform, it may not matter, but it's not representing the scope screen. With a trigger delay at 0, it means that the 320 microseconds of memory are split into 160 microseconds of data recorded before the trigger and 160 microseconds after the trigger. Before moving on, I like to show that the screen with respect to the memory is not always the same size. That would be way too easy. As I move to faster time-based values, the screen shrinks to almost nothing. We can move the trigger point to the right, shown as negative numbers, and the scope using normal or auto trigger mode keeps updating the memory accordingly. Eventually we reach a hard stop at minus 160 microseconds in this case. The reason that this is a hard stop is because now the entire memory is used to record data that happened before the trigger. This may be a bit confusing, but you need to keep in mind the original setting of plus minus 160 microseconds, so adding the negative 160 makes the most right point 0 and the most left point minus 320 microseconds. With a setting of minus 160 microseconds, you can see all events that happened in the 320 microseconds before the trigger, but nothing of what happened after. From a point of indexing into the memory for the visible screen, there's no change. When moving the trigger point to the left, the software thoughtfully stops automatically when reaching 0, and you need another second push to get it going into the other direction. You may be surprised because there is no hard limit, and we can go on and on and on moving to the left. Well, probably there is a limit somewhere, but it's so huge that you're unlikely to hit it, because the only way to move is incrementally. The reason why there isn't a hard limit is that all this does is adding a time delay which isn't limited by the memory. Let's say we had pushed the delay to plus 1000 microseconds. Using the same calculation as before, we find the right end of the memory represents now 1160 microseconds after the trigger, while the center is exactly 1000 microseconds and the left end represents 840 microseconds after the trigger. All the time from 0 to 840 microseconds, the scope is not storing anything, which is why that positive delay can be basically made arbitrarily long at no extra hardware cost. Anyway, before moving to the more complex case of single trigger, let's have a quick look at the waveform in the spreadsheet. For that, I'm saving the data as a waveform. In the interest of time, I show that as a result only, it's complex enough. On the upper left, you see the complete memory, all 8000 entries. And on the upper right, you see the same plot trimmed to the visible screen area. The actual screen is shown below. It is close but not perfect. The screen area plot appears slightly shifted to the left, which you can clearly see in the enlargement. I would expect the vertical line at or very close to 3999, but it's offset by 45. Not much, but noticeable. I don't have a good explanation for this other than my hunch that the scope wasn't using the full 8000 entries. I noticed a couple of times that the most right 20 or 50 entries or so sometimes contained junk. Even in this plot, there are oddities on the most right of the full memory graph, and at least the last 20 entries are not correct because that last vertical line should go all the way to the negative. If the memory area used is indeed slightly less than 8000, this would shift the midpoint to the left away from 3999. However, if the full memory is short by just 20 entries, the shift would be minus 10, not minus 45. Okay, the problem isn't a large one, and at least in the visible screen area you have always valid data, but I'm interested what causes the deviation. If anyone has a good explanation, please leave it in the comments. Okay, so far this was using auto or normal trigger, which keeps refilling the memory. Things are different in single mode or when no trigger events happen in normal mode. In this case, the scope switches to a different behavior when moving the trigger offset. Initially, when the trigger offset is 0, all is as it was before. The triangle in the middle shows the trigger position, dividing the memory into minus 160 microseconds before the trigger and plus 160 microseconds after the trigger. The memory indexes are also as they were before, with a visible area from 1000 to 6999. Once you start incrementing the trigger offset, you realize that you are actually not changing the trigger position because the little triangle doesn't move relative to the memory line. Instead, you are actually sliding the center of the visible screen area. It comes to a hard stop when the center is in the position corresponding to the memory position for plus 160 microseconds. From a memory index point of view, the visible area now reaches from 5000 to 10,999, but of course there isn't enough memory, which is why half the screen is blank. Going into the other direction produces similar results. I'm sliding the visible screen area to the left, past the unchanged trigger point, and finally reaching a hard stop, leaving again a half screen empty. The memory indexing bears this out with a theoretical screen going from minus 3000 to plus 2999. To summarize, in this mode, moving the trigger point by entering a positive or negative delay doesn't actually change the trigger at all. Instead, it is used as a screen offset to move the center of the visible screen, and the software is just reusing the trigger delay mechanism and readout for that. Using the same data field for two different purposes has the predictable consequence that if you leave the screen offset, like here on the extreme negative, and the trigger fires, it now takes that screen offset as a trigger delay for the new acquisition. If I scroll the screen window, oops, wrong direction, I wanted to go to the right. So we can see it corresponds to 0 now. And of course, if we go all the way to the left, the center of the screen is now at about minus 320 microseconds as we expect. This makes it clear that the whole of the memory contains now pre-trigger data. This might not what you wanted, so it's good to be aware of the issue that offsetting the screen also causes a change in the trigger delay when the trigger fires next time. Let's move back close to the right side. I stop at an arbitrary point near the right end of the memory at an offset of minus 100.8 microseconds. And let's have a quick look at the waveform in the spreadsheet. I'm going through the usual method shown before of selecting the data block and then graphing it as an XY plot. Since we are going to play with changing the plot position on the x-axis, it's useful to also freeze the y-axis scaling to prevent it from automatically changing the vertical scale. If you don't do this, the plot is harder to compare with the screen picture. If we enlarge the right side of the plot by plotting it from 7900 to 7999, we see some chunk from 7960 onwards. Clearly, this jump from full low to full high cannot be correct, since the next stair cycle would start very low at the bottom, so we should not look at data beyond 7960. And I'm going to delete these entries to not confuse us any further, and restore X-scale to the full range. Let's make a copy of this plot and arrange it so that we compare the picture on the screen with the full memory one. On the second plot, I'm going to change the range to the values you have seen earlier. The plot range goes from 2481 to 8480. Yes, this looks exactly right. You may wonder, how did I know those coordinates in the first place? I made this calculator spreadsheet that you can download from my GitHub page, link in the description. On the left, you see the two columns, time division and samples per second. These are the ones that determine which row to use. For convenience, I put them there in the form they appear on the scope screen, but for use in calculations, they are duplicated, this time just as numbers in columns C and D. The next column E tells you how long in seconds each sample is. Column F shows how long it takes to fill the whole 8K memory. Column G shows how long it takes to fill the whole screen. This number is smaller than the memory, sometimes much smaller, because as I showed earlier, the faster the time base setting, the smaller the screen gets. This is also reflected in column H, which shows the screen length in entries in the memory. It is mostly around 6000 entries, but at the fastest time base, the whole of the screen spans just 15 entries in the 8000 entries memory. So far, these columns are just static, driven directly by the selected time base, which also automatically determines the sampling rate. The next 3 columns show where the screen starts, the midpoint of the screen, and the endpoint in terms of their index values in the memory, while column M shows the time value associated with the most left 0 index of the memory. These 4 columns are driven by the values you enter into the green and red fields, which are the only fields that should be changed. Make sure that these are normally both set to 0. The green field is to be used when the scope is in the run mode. Here you enter your selected trigger delay, if it isn't 0. What this does is to calculate a new value for column M, the time associated with the 0 index of the memory. For example, earlier we discussed having a huge trigger delay of 1000 microseconds, which changes the memory start time to 840 microseconds. You can use the values of column E and M to associate a time value with each memory position, as I will show later. If you are in the stop mode, you can use the red column to type in the value used for shifting the position of the screen window, and this will calculate the new screen index values for left, middle and right. For example, just now we had a trigger delay of -160 microseconds and a screen middle position of -100.8 microseconds. This not only calculates the new memory start time of -320 microseconds, but also the new coordinates for the screen. The red warns that this value is outside the valid memory range of 0 to 7999, which means you should truncate it to stay within that range. The scope simply shows nothing in that area. Before leaving this spreadsheet, I want to highlight that for large numbers of settings, the screen area is actually 6000 entries or sometimes even 7500 entries. Each entry is an 8-bit sample. This made me wonder how the O1PC utility gets away with updates of less than 2K file size. 6000 entries for 2 channels should be a file size of more than 10K. I did have a closer look at those binary files, and it turns out the utility is always sending 600 samples per channel or less. I suppose that for cases where 6000 are needed for a full screen, they simply send only every 10th value. Another reason that I'm not a fan of that application. To finish up, I thought it might be interesting to see the scope's waveform at an extreme for this 70 MHz scope, that is 66.66 MHz. That should result in 4 complete periods on the screen and in the plot of the CSV file when done at the right position. From the calculator spreadsheet, we see that these positions should be from 3993 to 4007. While here, we should also note that the memory starts at -16 microseconds and uses 4 nanoseconds per sample. For the plot of the wave, I selected to show the points connected with straight lines, so it's obvious how few points make up the waveform at this frequency. Of course, the scope smoothens this using interpolation, and I can do similar things in the plot options, which makes the plot much more recognizable, but we must be aware that in doing this, both plot and scope screen are pretending that there is more data than there actually is. Another thing to note is that the screen does not show 4 complete waves. This illustrates the problem that my calculator spreadsheet is close, but not, for some reason, 100% exact in calculating what the scope shows. If I correct the 3993 to 3994 and the 4006 to 4010, the plot is much closer. Of course, one of the issues is that at this time base, changing the plot index by just 1 unit has a huge impact on the displayed picture. And just for completeness, you can, as I did here, add a column called time between the index and the voltages. For the first entry at index 0, you enter this formula in which the -16 is the time value in microseconds for memory index 0, and the plus 0.004 is the 4 nanoseconds expressed as microseconds from the time for each sample. If you recall, both of these values come from the calculator spreadsheet. Then it's just a matter of copying that formula for all remaining 7,999 entries, and now each entry has the correct time value associated. This allows you then to use time instead of index values for the x-axis, like in this plot of the first 16 entries. Initially I wanted to add doing Fourier analysis using exported CVS data. As you can see from this plot, it works quite well, but as this video is too long already and Fourier analysis is useful for other scopes besides the O one, I leave that for another video. If you have not subscribed already, hit that button and the notification bell so you don't miss the next video, and maybe consider becoming a Patreon, link in the description. As Patreon you get early access to videos, a blog and other exclusive content. Thanks for watching.